Hey everyone, so today we're going to talk about something you've seen a million times, probably since you were a kid, the number line. It seems so basic, right? A perfect ruler for every number you can possibly imagine. But what if I told you that this simple tool is actually hiding a deep, fascinating maze of paradoxes and, well, assumptions? Let's dig in and see what's really going on. So the big question we're tackling is this: is the number line really a continuous, unbroken line? Like, does every single little point on it actually correspond to a number we know? The answer is way more surprising than you'd think.
Right. So here's the version we all learned in school. Zeros in the middle, you got the positive numbers marching off to the right, negatives to the left. It seems to neatly organize every real number, from whole numbers to all the fractions and decimals in between. It's basically the foundation of how we picture math.
But let's start poking at that foundation a little bit. First stop on our tour is this idea of completeness. Is the line really packed solid with numbers, or are there gaps?
Okay, so before we can even talk about gaps, we need to get our heads around a concept called density. A set of numbers is called dense if no matter how ridiculously close two numbers are, you can always find another one to squeeze in between them. And the rational numbers, all the fractions, they're the perfect example of this. You can pick any two fractions, say 1/2 and 1/3. You can always find their average, which is another fraction that sits right there between them. And you can just keep doing this forever and ever, which creates this really powerful illusion.
If you can always find another number in between any two, then it seems obvious, right? The line must be completely full of fractions. There can't possibly be any room left for anything else. Or can there?
Nope, wrong. It turns out, even with infinitely many fractions packed infinitely close together, there are still holes. And these holes are what we call the irrational numbers. Numbers that you just can't write as a simple fraction.
So how in the world do we know these holes actually exist?
Well, one of the most elegant proofs in all of mathematics shows us how, using this clever trick called proof by contradiction. It works like this. You start off by pretending that the square root of 2 can be written as a simple fraction. But as you follow the logic, which you can see laid out here, you eventually run into a conclusion that's just impossible, a total contradiction. And when that happens, it means your starting assumption had to be false. The square root of 2 just can't be a fraction. Boom, it's one of those holes.
All right, so if we have all these holes, how do we fill them in? Well, a mathematician named Richard Dedekind came up with this brilliant idea. Imagine you have an infinitely sharp knife. A Dedekind cut slices all the rational numbers neatly into two groups. Everything in set A is smaller than everything in set B. That slice itself, that perfect line between the two sets, is what defines a real number. It perfectly plugs a hole like the one where the square root of 2 lives.
Okay, so we've filled the gaps. The line feels whole again. But our little trip through the maze isn't over. Now we're going to head to the other side of the map, the world below zero.
I mean, the number line makes negative numbers look so obvious. You just keep going left. Simple. But for centuries, this very simple picture caused huge philosophical arguments because it clashed so violently with the basic rules of arithmetic. Just check out Arnold's paradox. Your intuition says that the ratio of a big number to a small one, like 5 divided by 2, has to be bigger than the other way around, 2 divided by 5. Makes perfect sense. But what about 1 and -1? Is 1 over -1 supposed to be larger than -1 over 1? Algebra says they're both just -1. They're equal. This completely shatters our basic intuitive idea of proportions. The great mathematician Leibniz basically came along and said, look, you have to trust the system. He argued that you just have to treat these as abstract, symbolic calculations. The rules of algebra work, even if they feel weird or go against your gut. You just follow the rules, kind of like how we handle imaginary numbers today.
But some mathematicians took it even further. A guy named John Wallis was looking at what happens when you divide numbers right as you cross over zero, and he came to an even more bizarre conclusion. He argued that the ratio of a positive number to a negative one was actually a value that was greater than infinity. And this wasn't just some wild guess. You can see here in this slide, Wallis was using geometry from his work on infinitesimals to reason it out. He saw that as a series of fractions gets closer and closer to zero, from the positive side, it shoots off to infinity. So, he thought, if you just keep going past that point into the negative numbers, you must be going past infinity.
It's a totally mind-bending idea that just shows how tricky that left side of the number line really was.
So, we've got holes in the line that need to be filled, and we've got paradoxes lurking below zero. All of this leads us to the most fundamental, most important question of all about our so-called perfect ruler.
We just kind of assume that for every single point on this line, there is one and only one real number that matches it perfectly. But is that a fact? Is it something that can actually be proven from the ground up, or is it something else?
Well, according to this comment from a discussion board full of mathematicians and physicists, the answer is no, not really. In classical Euclidean geometry, the stuff based on what you can build with a straight edge and a compass, you simply can't prove it.
And the reason why is that Euclidean geometry can only pinpoint a special group of numbers, the constructible ones. It has no way to find what are called transcendental numbers, famous ones like pi or e, which go on forever without repeating and can't be created with simple algebra. To classical geometry, they're basically invisible.
And this comment right here gets to the heart of it all. What if we just define it as being true? What if this perfect link between points and numbers isn't a theorem that we prove, but an axiom that we just start with?
And that, right there, is the ultimate secret of the number line. The complete, gapless line that we use every single day isn't something that was proven from ancient geometry. It's a foundational belief, an axiom. We accept that it's complete as a starting point, because it's what lets us build all the powerful tools of modern calculus and analysis.
And that kind of leaves us with a final thought, doesn't it? The simple line that we can draw in the sand is actually built on a really profound assumption. It makes you wonder, what other simple truths that we take for granted are actually powerful axioms, foundational beliefs that shape our entire understanding of the world? Thanks for joining me on this one.